Hello everyone, my name is Hanao. In today's presentation, I will talk about our work enforcing sparsity on the latent space for robust and explainable representations. Currently, latent generative models have gained increasing popularity. Most of them are using dense latent variables and have achieved great performance when generating new images. But the dense latent variables are sensitive to noise, and they do not have interpretability. On the other hand, sparsity can have concise representations and can lead to increased explainability and robustness. At the same time, current approaches mainly use variational-based method. They use an encoder to approximate the posterior, and it may lead to inaccurate inference. With the above limitations, we are interested in proposing a new latent generative model with one generator network only, and at the same time, it can have sparse latent variables. The joint distribution of the latent generative model is related to the conditional distribution and the prior. We propose to use spike and slab distribution as our prior belief. It consists of a direct delta spike variable and a continuous slab variable. In order to maintain differentiability, we adopted a Gaussian distribution with small variance to approximate the direct delta function. So now our prior is essentially a Gaussian mixture model. And then for the generative model G that maps the latent to the observation is also a Gaussian distribution with mean G of Z and also the variance sigma square. And the generator G is parameterized by a top-down neural network with weights theta. To train our generative model, we can use maximum likelihood estimation, but notice that when we take the derivative with respect to the objective, the expectation term is intractable. So we will have a two-step training scheme that involves the inference step and the learning step. To calculate the expectation term, we can use long-run dynamics to sample the posterior. Theoretically, when step size is small enough and the number of steps approach to infinity, the marginal distribution of Z can asymptotically converge to the target posterior distribution. So in our case, to better align with our objective, we use zero initialization, and it can lead to improved performance comparing to initializing from other distributions. And now we have sampled the posterior, we can use the complete data model to update the network weights using gradient descent. But in the case of sparse representations, averaging samples over the objective may lead to learning repeated features. So we propose to obtain multiple samples along the Markov chain trajectories and select the sample that can best reconstruct the original images, such that the developed features can be reused and learned latent code can be more informative. In terms of the theoretical understanding, the log of the spike and slab prior can be rederived into the following form. Assuming C1 is the component of the standard Gaussian distribution, and C2 is the component of a Gaussian with smaller variance, we can notice that when the latent variable Z is small, it is more likely to be coming from the second component. So the probability of C2 given Z will approach to 1, and the gradient of this term will approach to negative Z over sigma 2 squared. It implies we will have a larger gradient for smaller value Z. So if the latent holds inconsequential information, the prior term will penalize it and enforce them to go towards 0 and lead to sparsity to a certain degree. Next, we conducted extensive experiments to demonstrate our model's performance. First, we show that our model can effectively enforce the sparsity on the latent space. In the figure, we see that as we decrease the level of alpha, more and more latent dimensions are pushed towards 0, and at the same time we can keep the same reconstruction compared to the dense latent variables. With alpha equals 2.01, only a small subset of latent dimensions are active. From the left figure, we can see our model can faithfully reconstruct the original images, and from the table, we can have the best peak signal to noise ratio compared to other sparse models, while being competitive to the dense models whose latent dimensions are all activated. We then show the explainability of learned latent representations. In the left figure, we demonstrate how changes in the disentangled factors, such as facial features and expressions, can be observed while keeping other features unaffected. The learned latent codes have shown their ability to discover disentangled factors from the training datasets in an unsupervised manner. In the right figure, we plotted the heat map of the learned latent representations for fashion MNIST data. We can clearly visualize the learned latent structure for each fashion class. Each category forms an apparent pattern with only a few activated codes, while most latent dimensions remain inactive. Objects with the same category have similar activated latent maps with small variations. This makes the learned latent representations more interpretable when altering their latent code. We then show our model's generalization ability using sparse latent codes. In the left figure, we used only 500 MNIST training samples to train the latent classifier. We noticed that our learned sparse representations can have the best performance in terms of the classification accuracy. It can also increase the robustness of the classifier, and as the dimension increases, the classifier will not overfit compared to other dense models. We also verified our classifier results by plotting the t-SNE visualization graph in the right figure. We can see the sparse latent representations learned by our model can be well separated into different clusters. The ability to separate the clusters implies that our model has captured pivotal knowledge of each class, leading to a more robust classifier. We further checked our latent code's robustness against the standard Gaussian noise. In the left figure, we can observe that for short-run DES and VSE models, they will recover the round digits when the noise variance is high. At the same time, our model at the bottom row can accurately recover from the Gaussian noise and obtain the correct digits. In the right figure, we also checked the denoising effect on the SVHN and the SLEEP dataset. With different level of Gaussian noise, our model can reconstruct the corrupted faces and the digits without changing too much of the original information. This implies that the learned sparse representations can be robust to Gaussian noise, and the added distortion from noises does not have much impact on well-learned latent codes. We also checked the quantitative results of noisy images using latent classifier and the structural similarity index. Our model can outperform other related works in both tasks. It shows that the learned latent representation can lead to increased robustness. In this paper, we present a new learning method to learn sparse representations for latent generative models. Our model can perform exact inference without the need to design an extra encoder. We are able to demonstrate the learned sparse latent representations can boost the robustness and explainability in the tasks of denoising and classification. But at the same time, there are also some limitations in our work. For example, since we are using Gaussian mixture models to approximate the behavior of the direct delta function, inactivated latent codes are actually very small numbers but not zero. And since we are using Markov chains, and it can take longer to infer the latent variables. And we may further explore this area and try to solve these limitations and improve the current model. And this will be the end of the presentation. Thank you very much.